Hi, it's Kai Olumide, and today we're gonna be solving another one of the most commonly asked tech interview question. It's the longest uniform substring after replacement. It's a commonly asked DSC question by top tech companies including Google, Amazon, Meta, Apple, Microsoft, Netflix, and other top tech companies. The problem statement states that a uniform substring is one in which all characters are identical. Given a string, determine the length of the longest uniform substring that can be formed by replacing up to k characters. What this problem statement is trying to pass across to us is that we are going to be given a string and we are asked to determine the length of a substring in the string that actually consists of unique identical characters, the same set of characters, and we are given an opportunity to replace up to k characters. So if we look into this string right here, we are gonna say we have a b c d c c a, and by we are given an opportunity to replace two characters, k characters, where in this case k is 2. So if we replace the character right here at b and at d, we're gonna be having a c c c c c a, and therefore we see that the length of the longest uniform substring is actually 5. You understand? Because right from the first c to the last c, which are 5 in length, is a substring of s of the string. You understand? And it actually have a uniform and identical set of characters, so, and it has the highest length so far, so that's why we're returning it. So that's what the problem is just trying to pass across to us, is to evaluate the a substring of x that tends to have the longest length and also tends to be identical in characters. So, and we are given an opportunity to replace up to k characters. So as you can see in this example explanation right here, we say if we can only replace 2 characters, then the longest uniform substring we can achieve is CCCC, which is obtained by replacing the B and the D right here. So it's gonna be the longest we can achieve so far. Now, before actually finding the longest uniform substring in S, let's try to look at the most efficient way in making a particular string uniform by having the least or the fewest number of replacements, because that is literally what we are asked to find here. It's just like trying to look out for the set of uniform substring that can be formed by replacing up to k character and then returning the longest of them also. We need to find first the most efficient way of making a string uniform by replacing the least number of characters. Let's consider this example. Now, what characters in this particular string ABAC should we replace to ensure that the least number of replacements is performed, or the minimum number of replacements is performed before the string becomes uniform? We are gonna see that A in the string, the character A has the highest frequency in this particular string, and because of that, to make this particular string uniform in the least number of replacements, we are gonna be changing everything except A. So because except A, we just have to change B, B, and C. You understand? But imagine if we are gonna be choosing B over the rest of A and C, we have to be changing every occurrence of A first and then C, which means that we are gonna be having 4 replacements, at least 4 replacements. But having A with the highest frequency, to make the replacements, we just have to change just 3 character in this particular string, and therefore A makes up the least replacement to obtain a uniform string in this particular scenario. A key observation here is that the minimum number of replacements that is required to obtain a uniformity in the string, in this particular string, is obtained by changing and replacing every other character except the most frequent one. Look at in this case now, A is the most frequent character because it occurs and has a frequency of 4. It has a frequency of 4. So, and because of that, because it's the most frequent one, to obtain a uniformity, we are gonna change every other character except from A. So that way, we just need to change the first B and the second B and then the C right here. So, and that's the least replacement we can have by replacing every other character except the most frequent one. This suggests that if we know the value of the highest frequency of a character in a string, then we can determine if our value of k is sufficient enough to make the string uniform. What I'm trying to say in essence is that if right now in this string we know that the highest frequency is 4, the value of the highest frequency of the character is 4 because A actually have the highest frequency and its frequency is 4, and because of that we need 3 replacements to make the string uniform. Why? Because actually the length of the string is 7 and then the frequency of A in the string is 4, so we need 3 replacements to get the job done, to get the string uniform. And because of that, if k is up to 3, then it is possible that we obtain a uniformity in the string. Don't forget, k is actually the value that is given to us that we can make up to k replacements. So therefore, to find the number of characters that we are going to replace, you understand, so we can have that by subtracting the length of our string, or let me say subtracting the highest frequency from the length of our string. In this case now, the highest frequency is 4 because A occurs 4 times and the length of the string in total is 7. So 7 minus 4 gives us the number of character to replace. Once we have access to the number of character to replace through this subtraction, we can therefore conclude if our given string can be made uniform. So if the number of characters to replace is less than or equals to k, then we can obtain a uniformity because k is actually the total replacement that we can do, that we are opportuned to make. You understand? So, and if the number of characters to replace is lesser than or equals to this number of replacements, definitely we can obtain a uniform string. But in a situation whereby the number of characters to replace is greater than the opportunity, the opportunity to replace up to k characters, definitely there is no way we are gonna obtain a uniformity in the string. Now, to calculate the number of characters to replace, we are going to need the value of the highest frequency. So, and what that means is the highest frequency in the string. Just in this case, A has the highest frequency and the highest frequency is 4 because A occur 4 times in the string. So, and that means that to obtain the highest frequency, we need to keep track of each character in the string, and we can efficiently do that and manage that using an hash map. The hash map is gonna allow us to update the highest frequency whenever we encounter a character with a higher frequency. Let's use this example below to explain how the hash map works and how the frequency tracker works. So let's say the first element, the first character in our string is A. So we're gonna have our hash map, the frequency hash map, to track it, and it's gonna be a key to value where the key will be the string or the character in that character in the string and the frequency. So we know so far A have only occurred once because we are at the very start of the string, so its frequency will be 1. So, and right now the highest frequency will be 1 because it will be the maximum between the previous highest frequency and the frequency of the current character. So don't forget, by default highest frequency will be 0. You understand? So and once we are on this particular character now, the maximum between 0 and the current frequency of A, which is 1, will be 1. So high frequency is currently 1. So what we do again is that we transverse to the second one. So it's supposed to be here, and when we transverse to the second one, we see that B will be added to the hash map and B will be 1. So and at the same time, highest frequency is still gonna remain 1. You understand? Because it is previously 1. So maximum between 1 and 1 is still 1. So now it's gonna transverse to the third one, like you can see right here, and at this point it's still B again. So the frequency of B will increase by 1 in the hash map, and it's gonna be 2. And now the highest frequency between the previous highest frequency, which is 1, and the new frequency of B, which is 2, the maximum is 2. So that maximum is gonna be the highest frequency. So and when we move again to the last item, or the last character in the string, is a C, and because the C has a frequency of 1, because we're just encountering it for the first time in the string, highest frequency is gonna remain 2, which is the previous highest frequency. And if you look at it, logically you will see that it is actually 2, because out of this the highest frequency is that of B, which occurs twice in the string. Now that we have the tool to help us determine if a substring can be made uniform, so the next step is to actually determine the longest substring in the string S. You understand? So fine, we can now determine if a particular substring in S can be made uniform. You understand? So now we want to know the longest out of every possible substring that can be made uniform, and we are going to do that using the dynamic sliding window technique. Why we'll be using the dynamic sliding window technique is because we actually want to find the longest subsequence, or let me say longest substring that satisfy a specific condition. So we are not given a fixed length. Unlike fixed sliding window technique, we want to find the longest, so we need to be able to shrink and to expand along the way, so to find the longest in the string S. So we're going to be using a dynamic sliding window technique, and we are going to be using this particular condition to determine if the dynamic window is going to be sliding or shrinking. So depending on the condition, that the number of characters to replace for a particular or a given substring must be less than or equals to k. If it is less than or equals to k, if the condition is met, we are going to expand the window to find the longer window that still meet the condition. So but in the situation where the condition is not met, we are going to shrink the window until it meets the condition again. So we are considering some possible or all possible substring of our string S, and then we are trying to look if each of these substring meet this condition. If it does, we expand the window for a more longer window that would meet this condition. If it does not, we are going to shrink the window until it meets it again. Let's see how this works over this particular example here. So we are going to position our left and right boundaries of our window at the first element of the string, and now we are going to check if this particular window satisfies the condition. So right here we know our highest frequency is 1, just like we discussed above. So by using a hash map, we keep track of and we see that A just appeared for the first time, so its frequency is set to 1, and that's our highest frequency. So and then the number of characters to replace will be dependent on the length of the window minus the highest frequency, and that's 1 minus 1 because the highest frequency is 1 and the length of the window is just 1, and then that gives us 0. 1 minus 1 is 0. So we don't need to replace any character for now, and that is 0 is less than k, which is the total number of replacements we are opportune to do. And because of the number of characters to replace is 0 and it's less than k, we are gonna keep on expanding our window, and we did that right here. We shift our right pointer by 1 to the right to expand our window, and now we fall into another A again. So our highest frequency is now 2 because in our frequency hash map is consisting of A, the key A, to value 2, because A occurs twice. And now the number of characters to replace, we're going to calculate it as the length of the window, which is now 2, minus the highest frequency, which is also 2. And so far we have no character to replace. That gives us 0, and 0 being less than k, we're going to expand again. And right here we expanded again to the right by 1. So, and so far we added a new b key value pair into our frequency. B now occur 1, so its frequency is 1, but so far our highest frequency is still going to remain 2, which is the 2 times that a occur. It is the highest frequency, and because of that we can now calculate our number of characters to replace by subtracting the highest frequency from the length of the window, which is now 3, and the highest frequency is 2, so that's 3 minus 2 and 1. So far the number of characters that are going to be replacing is 1, and logically you will see that it is b. So, and because 1 is still less than the k, which is the number of replacements we are opportune to have, it will be given to us in the problem statement. And because 1 is less than k is actually 2, so we're gonna expand. So expanding again, we expand the window. Now the window length is 4, and now we have another particular character c inside our window length. So that still left the highest frequency unchanged. High frequency still remains 2, which correlates to the first 2 character AA. So it's still the highest frequency so far. And now to calculate our nums of character, we're gonna do 4 minus 2, and that gives us 2. And we're gonna expand again because, well, we still have the grace, because it is not greater than the opportunity that is given to us for replacement. It still equals to it. So, and now expanding, it moved from C to D, and now the window is now of length this 5, and you will see that the higher frequency still remains 2, because there have not been any higher frequency than 2. It's still A that occurred twice. So, and because of that, to calculate the number of characters to replace, now we have it to be 3. Yeah, because the length of the window is 5 and the higher frequency is 2, so we have 3 characters to replace, B, C, and D. And because of that, we need to shrink, because that's now greater than the opportunity that is given to us for a replacement. So, and because we need to shrink, we're going to be shifting our left pointer by 1 to the right to shrink the window, and that dramatically reduce the the window length by 1. So the window length is now 4, but the highest frequency still remains 2, so which is actually not correct, because the 2 that is in with the highest frequency is due to A occurring twice at first. Now that we have our left pointer shifted to the right by 1, we have left this A, so it's not supposed to be 2. But so far, the algorithm and the logic that we know and we talked about concerning the highest frequency is that it increases when it comes across a character with higher frequency, or it remains constant if it comes across a character with its lower frequency than the previous highest frequency. So we actually have not updated our logic to update highest frequency whenever we drop a character. One way to work around this is actually to update our highest frequency, to go about a logic and to think of how we are gonna decrease the highest frequency whenever the frequency of a character drops. You understand? But our goal is to find the longest substring that meets the condition of replacement that we discussed in the logic. So shrinking the window will not actually be of any benefit to us. We actually want the longest subsequence, and so far we found the longest subsequence to be A, B, C, and just before it gets to D, where the number of characters to replace exceed K. So really we're not interested in shrinking. Rather we just want to slide over. So after we find the longest subsequence, if it is violated, we want to slide over. So because we are only interested in a length, or in a window that is more broader than that, fine, we found a length that is 4. Now we are hoping for a length that is 5 or 6 or 7, not actually shrinking. So we can just be more optimized by sliding the window instead of shrinking, sliding it the window. So we are going to be sliding the window whenever the window violates the condition. So that way we are going to be effectively managing the length of the window, and that way we won't get a lower length than we have previously gotten. We only get a larger and longer window as the problem statement wants. So now let's update our previous logic that we said. Okay, concerning dynamic sliding window technique that we discussed, the previous logic is that if the window satisfies the condition, we should expand it for a more longer window, and if the window does not satisfy the condition, we should shrink it so until satisfied. But we are not interested in shrinking, we just want a larger and longer window. So if the window does not satisfy the condition, we are going to slide so to the next possible substring of that same length, so to check if it's going to satisfy the condition. So let's correct the action that was taken in the first invalid window, so the other time, whereby we shrink instead of sliding. So right now we are going to be sliding instead of shrinking the window. So this time we slide to the next possible substring in the string. So, and by sliding now, we can see that the highest frequency in this particular window that we slide into now is 2, and now it's different from, right now we don't need to keep our highest frequency, we don't need to dwell on the past highest frequency, because we slide now we are gonna create a new highest frequency based on the new characters in the window. So, and at this point the characters are A, B, C, D, C. So we see that A occur once, B occur once, C occur twice. So highest frequency is 2, D occur once. So highest frequency is 2 so far in this particular window, and because of that, our number of characters to replace will be 5 minus 2, because the length is 5. So length of the characters here is 5 and length of the window is 5. So 5 minus the highest frequency is 2. We see that 2 is 5 minus 2 gives us 3, and 3 is greater than k, is greater than the allowed replacement from the problem statement. So we are going to slide again, so because we don't want to shrink, we're not interested in a shorter window length. So shrinking now, we shrink to this we slide, we are going to sliding now, we slide to the next subsequence. You will notice that as we are sliding to the next subsequence so of that particular length. So we want to just consider subsequence of this length now. So sliding, we have B, C, C, D, C, C, and we see that C added increased in frequency. It added 1 frequency to itself, and now the highest frequency is 3, and because of that our number of characters to replace becomes 5. Don't forget the length is still 5, we just slide. So that will be 5 minus 3, which is 2. We see that now we satisfy the condition, because the number of characters that we have to replace are just B and D. So we don't have to be it is not greater than k, is not greater than the allowed replacement. So what we do again is that we expand this time around to a length of 6. So expanding to a length of 6, the highest frequency remains 3 because A is added, and C still holds the highest frequency. And to calculate the number of characters to replace now, that will be 6 minus 3, and that's 3. You see that 3 is greater than the k, the allowed replacement. So we're gonna slide, but we have gotten to the end of the string, so we are just gonna exit the loop and return the longest subsequence that can be made uniform by the k replacement, which is 5. Don't forget it is A, B, C, 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 because by replacing A and B, we can have 5. By replacing B and D, we can have 5 subsequence with the same identical character C. So, and now you know that is because as we are traversing the window, we are going to be keeping count of the longest window, and we can get that by doing right minus left plus 1. So that way we are going to keep count of the longest valid window as we are traversing the string. So this is the logic that is required in solving this problem. So we are going to be going into the code implementation, but let me just quickly summarize the logic. You place your left and the right pointer at the very start to represent the boundary of the window, and then you start to traverse the window to expand it by moving the right pointer to the right, and make sure you are checking at each point if it satisfies the condition. So if the condition is satisfied, if the number of characters to be replaced is still less than or equals to k, then you expand your window by shifting the right so as to get at a more longer window that satisfies the condition. But if it does not satisfy the condition, we actually slide to the next substring of that same length, so we can effectively manage that length. And so we try to check if it satisfies the condition. If it does, we expand it again. So, and along the way, we are making sure we are keeping track of the length of the window. So because the length of the window is gonna tell us the longest the maximum length of substring that satisfy that condition so far. So, and that's what we're gonna return eventually. So we're going to be going to the code implementation now. Kindly follow along. Now let's go into the code implementation. We're going to be defining the function, and we're going to call it the longest uniform substring after replacement. So it's going to be collecting a string s, which is the string that I want to find the replacement in, and also k, which is an integer that tells us the number of replacement that we are opportune to have. And the return of this function is going to be the length of the longest possible substring that contain identical characters. So right now let's define our frequency and hash map that we hold the frequency of each character in the substring of x. So we're also going to be defining the highest frequency of each substring or of each character in the substring. So, and also the maximum length that's going to keep track of the maximum length of the substring with the longest identical characters as we navigate through the string. So they will be set to 0 initially, and now we have our left and the right pointers that is situated at the first in the 0. So now while right is less than the length of our string, so that way is gonna ensure that once right become equals to length of string, we're gonna exit the loop. So what we want to do is that the particular element at this particular element at this position in the string, which is at right at the position 0, we want to add that frequency, its frequency into our frequency hash map. So frequency of s of right, we want to update it is equals to frequency of s of, let's say, frequency dot get. So s of right comma 0 plus 1. So we're trying to update it inside our frequency. So anytime we encounter a character, probably a new character or an existing character, we want to make sure it's updated inside our frequency, and that's what we did right here. So if it is not there, it's gonna set it to 0 and increment it by 1. So if it's there already, it's gonna increment it by 1. Now let's update our highest frequency. Our highest frequency is the maximum between the previous highest frequency, which is which default to 0, like we initialized. So highest frequency and frequency of s of right. So the maximum between the highest frequency and this new updated frequency now, because who knows, this one might be an existing character that just incremented. So we want to make sure that highest frequency is updated to the highest frequency in the frequency hash map. So doing this now, let's go on to calculate the number of norm of characters that is to be replaced in this particular window. Don't forget that left and right pointer actually signify a window, the boundary of a window. So our window is already created already, so we might decide to expand, we might decide to shrink, but definitely our window is created. So we want to know the norms of characters to replace in the window, and we can know that by doing right minus left plus 1, right minus left plus 1. So why we are doing this is because right minus left plus 1 actually is calculate or sum up to the length of the window. The current length of the window is divided by right minus left plus 1. So I want to subtract the length of the window minus the highest frequency. So that's gonna help us to calculate the number of characters to replace, just like we discussed in the logic. So if the number of characters to replace, if it is greater than k, then we need to slide our window. So, and we need to shift our left by 1 to the right. That's how we slide our window, by shifting the left and the right boundaries of the window. So but before doing that, we need to update the hash the frequency hash maps also, so that it's gonna remove, we are shifting it away by 1, we are removing a character, so we need to make sure that it is removed here inside the frequency, also inside the frequency hash map as well. So we do that like this. So don't forget, we have to do it before we actually increment our left, so we are going to be removing the right character. So after that, we can calculate the maximum length, update it to be the maximum between the previous maximum length. Don't forget, we're interested in the maximum, so we don't just want any length of a window, we want the longest length, we want to keep track of it. So that's why I'm using maximum between maximum length and right minus left plus 1, which actually signify the length of the window, current length. So, and after that, we are gonna expand our right by 1 now to move on. So you will notice that we first calculate the maximum length before shifting our right. Why? Because we don't know if this new right will satisfy the condition, but so far the particular right before we shifted it has satisfied the condition, so we have to evaluate the maximum length for that particular window before expanding the window. So, and after doing that, we are going to return the maximum length. So, and that's it. So we're going to be defining, so let's define our parameters. I forgot to do that, so we should define our parameters first. So here I defined the S to be AA, B, C, D, C, C, A, like it is in the example and the example problem statement. So, and I set my key to 2, and now I'm calling the function. So let's run it. So right here we have 5 printed. Sorry, we have 5 printed right here. So you see, and that's truly the answer, because if you look at it now, by replacing B and D, we see that we are going to have 5 consecutive C in the string, so as a substring of S, and that's 5. So that's just the solution, and that's the logic to solve this problem. I hope you understand, and do well to like, to comment, to share and repost, and engage in any way you can. It's going to be of help to me and of help to you as well. So thank you.